Yes. So you should see this. Let me just organize my screen a little bit here. You should see PHP from. Is this readable for everybody? All right. So, well, a parser is fundamentally anything that takes some input, typically a string, but it could be anything really. It could be some other existing data structure. But we're only going to do strings today. But it takes some input and turns that into something more structured, so that we can do something useful with it. So it could be well, it could be something as like JSON or even an entire programming language, which is typically just text, and we want to turn that into something that a compiler can work with. And there's many ways to do that. You can there's grammar parser generators where you define sort of a grammar and then it turns it into code. Different ways of doing it. Regular expressions are parsers fundamentally. Parser combinators are sort of a different approach, and it's an approach that actually I now feel that like you could have invented this yourself. It's it has, in my opinion, a very sort of elegant beauty to it. So let's write the simplest parser that we can come up with. So our input is going to be A, and we want to parse the character A. So the expected output is also going to be A. Of course, this is not a very useful parser, but it's a start. So, or well, let's call that an A parser. It's going to be some function that takes some input. Actually, I'm not even going to use types, just to keep the code very compact. So it takes some input and it checks if that character is in fact the character we want. So we can have something like if the input equals the character A, then we return that character. And if not, we can, here in the simple example, just return false. So now we can actually try our parser. It's a function, so I can just pass some input here. So that would be our input variable. And this is our output now. And let's turn this into a little test. Assert equals expected, and this is our output. So if we run this, actually it's always good to watch it fail. So I will put in something else in there, character B, and now we watch it fail. So it returns false instead of the expected character A. Everyone still with me? Is this a good pace or? All right. So of course this is not very interesting yet, but it sort of shows the basic structure of a parser. It takes some input and returns either some useful output or fails. There's something else that is going to be useful. Actually, let's first add another one just to sort of see it work, right? We can have another one called a B parser, and that one tries for the character B. And so, well, this was the A parser, so let's do it like that. And move that below here. So it's like this. And our B parser is just doing the same thing, right? So it's asserting that, let me copy this. Well, I need all of it, right? So let me just do this. So the input is B, expected is B, and this works. This should work. What did I do wrong? I probably input expected. Oh, I know. I need to use this parser. That's what you get when you copy paste. All right, so this is still not very interesting, but it shows us that we want to actually generate these parsers instead of just writing them all by hand, because obviously this is all very, very similar. So I could write my own character parser now, which takes it's a function, and it takes the character that we're interested in as the argument, right? So this could be our character, and then it returns not the output yet, because well, I said earlier a parser is a function that takes an input. So this function is a function that makes a function that returns an output, right? So this is we call this higher order functions, but that's a concept in functional programming. It doesn't really matter for us here. But so basically we have a function that takes a character that makes a function and that now compares the input not to a hard-coded B, but to our character, and then returns, well, the input in this case. So we generalized into our car function, and now we can take all of this. Input could be anything here, and now this is, well, my parser. I still need to create the parser now, of course. So my parser is a car like this that takes a character X. And now when I run the parser, so that's this line here, on some input X, well, that's the input like this, we pass the test. So we can actually get rid of all this duplicated code. Is that making sense? So we have a function creating a function which is a parser, right? Which is going to be useful later, of course. So so far we can do very simple things. What we want, of course, is to create much more complicated parsers. Things that can do, you know, some basically DSL, a language for describing how our parser should work. And that's where combinators come in. So a combinator is really any function that combines other functions into something else. So for example, we want a parser that can, let's call it OR, that can take two parsers as arguments, and that checks if one or the other succeeds, right? So if the first one succeeds, we return the output of the first one. If the second one succeeds, we return the output of the second one. If both fail, we return a failure, basically. So how do we write that? Well, again, it's a function. It takes a parser, it takes another parser, and it returns a new function, because what we want is a parser function again. And a parser is always a function that takes some input and tries to return some output. So now we need to somehow combine these. So we can actually try our first parser on our inputs. And if that succeeds, we return the output of the first parser. So we can, well, we could write this again, but you're probably familiar in PHP with this. So we could do this and then the next part. But you're probably familiar with this notation, which is sort of a shortcut for if this succeeds, return the value of this. And if not, we try our second parser on the input. And if that one fails, then it will simply return the value of that. We could make that explicit like this. And that's our entire OR parser. So let's try it. So if we have, we still need to make our parser, of course. So we can say our parser is OR, well, let's say character A or character B. So we created, that's our first function here. We created, we call this function. So the output of that is now a parser function that takes an input. This one takes an input. So we can run it. Let's do it like this. So let's try it on A. The expected value is going to be A. We run our parser on the input and we expect that result. So let's try that. We can see that working. If we have B, it doesn't work because our input needs to be B as well. There we go. If our input is wrong, of course, then it should fail. Making sense? So this is our first combinator, right? This is a it's still not super practical, but you can see how this will be useful, of course, in the future, because we can now have choice in our parsers. It's actually a little bit more complicated. I said that a parser is a function that takes an input and returns some output, but that very much limits our options. What we want is to actually return some output as well as the remaining part of the input that we did not consume, because that way we can continue doing some work on that remainder of the string. Right here, our input was always a very short string, but if we wanted to do something like, I don't know, ABC, or it could be some format like, I don't know, A1, and maybe we want to separate these values out of there, right? So what we need is our parsers need to return both the consumed part, the part of the input that we matched, as well as whatever's left. Actually, I'm going to copy those two because they're boring codes from here. So I just wrote a quick head and a tail function to get the start of a string, and so head gets the first character of a string, returns the first character, tail returns the remaining part of a string. Just a quick utility function here, because now we can use this and say our character parser now, instead of trying to parse here we were comparing the entire input, right? But what we're now going to do is say if the head of the input is our character, then we return a pair consisting of the head of the inputs. And the other part of the pair is going to be the remainder, and the remainder is the tail of our inputs, like this. So now if we have, for example, something like input XABC, or expected output is the X, or expected remainder is going to be ABC. So let's call this one output remainder, and let's call this result. So when we run our parser on the input XABC, it will try the first character. If it succeeds, it returns a pair of the first character, the consumed part, and the remaining part. And then we want to see that here as our output and our remainder. And well, this is probably going to break now, so let me just turn that off. What did, oh yes, I know. We should use result here. Yeah, so now, well, we could inspect this if you want to see it. Or so our input was XABC, our output is X, our remainder is ABC, and our result is the pair of our output and our remainder. Right? So why is this interesting? Because now, of course, we can do something with the rest of that input, and make more interesting combinators that way. So let me get rid of this. Everyone still with me? Is this too fast? Is it good? All right. So, well, let's forget about the OR one and let's move on to sequence. So, for example, we want something now that says parse this thing and then parse this other thing. So that could be a sequence, which is another combinator, right? So it's somewhat similar to our OR parser. It takes a parser, it takes another parser, and then it returns a new parser, basically. Again, that's why it's called a combinator, right? You take two parsers, combine them into a new parser, and this just keeps on composing with parser combinator. So you can do arbitrary, complex compositions of parsers that way. So sequence, it's a parser, so it takes some input and is going to return a pair. Actually, I'm going to need to turn this into the old school notation because it's going to get a little bit more complex here. So, well, sequence tries the first parser. If it succeeds, it tries the next parser. And then if that succeeds, it returns the output of the second parser. All right, so let's just turn that into code. If my first parser, if I run that on the inputs, and in fact, I'll put that in, well, let's call it result 1. So result 1 is the result of running the first parser on the inputs. If result 1 succeeds, then we need to try the second parser. So result 2 is the outcome of running the second parser, actually not on the input, but on the remainder of the input, right? Because the first parser already consumed its own chunk of the input. It succeeded. It returns the output plus the remainder, and now we want to continue parsing on the remaining part of that input. So from result 1, we take our second. In fact, let's make that a little bit more explicit and label these. So output is the head, remainder is the tail, and maybe I should, I don't know if that's going to be more readable this way. Maybe like this, right? So a character parser is still the same, but instead of this this pair, it's now an associative array of output and remainder. So that here we can now explicitly say take the remainder. This is all not very pretty, but that's of course where the library is going to come in. So we run our second parser on the remainder of the first parser. We get our second result. We need to use that. Yeah, this is just including it here. And now basically if the second one is successful, we return again something of this structure, which is, well, actually we don't need to do that because our second result is already either a pair of output and remainder, or it's false. So I don't actually need to spell this out explicitly. I can just return.
Matthias, could you let the people who are waiting in, please?
Oh, how do I do that?
Just a couple of late showers in the bottom.
Okay. Yes. I think if I, let me try if I can make you co-host. No, it's like an option. You probably need to turn that on separately in Zoom, but let's not bother with that. So welcome to the people who are just joining. So basically we can here return R2, and if our first parser had failed, then we could just return false. And that should be our entire sequence combinator. So let's write some tests, right? So if my input is let's say ABC, and I make a parser that is a sequence of the character A followed by the character B. We can try this on some. We can try this on the input now. So our result is parser applied to inputs, and assert, no, assert equals. Of course, this will now have this, this structure here. So we'll have an output and a remainder. And this is our result. And a little pop quiz. Oh, this should be narrow. What are these values going to be? If you've been keeping up, you might have the answer. Anybody? So it's a sequence A, B, and our input is A, B, C.
I'd say B and C.
Let's try it. I hope I got it right. Let's see. Oh, that's the other one that is failing because this one doesn't have the labels. Let me just fix that here. And there we go. So you were absolutely right. So the reason it's B is, of course, because in this, the sequence combinator ignores the result of the first one and returns the result of the second one. So that's why we get B here. Of course, you're not always going to want that. Sometimes you're going to want to return, for example, an array of the two values that you matched, or some other stuff. But I hope this gives sort of a sense of the general approach to how these parser combinators work. It's the whole library is basically a bunch of sort of low-level parsers like char. So instead of writing your own stuff, you would well, let me add another test here. Yeah, whatever. We don't need a name. Oh, yeah. And so basically, a simple parser would look something like this. This is a function that's provided by the library. In fact, more realistically, you would do something like, for example, at least one is a combinator. You give it another parser, which could be, for example, alpha num char. And so this one will match, of course, any alphabetic or numeric character. And this one matches at least one of those and keeps going until it stops finding and then stops parsing. So the whole Parsica library is a bunch of these sort of low-level parsers and parser combinators. So if we and it also comes with some assertions just for practical reasons. So I can shortcut the whole thing into. Actually, let me show you first how it would work. It's basically the same thing that we have been doing already, of course, but so with a little bit more API around it. So we could use the run function, or maybe even better is the try string function. But basically, we try this parser on a string. For example, this could be ABC123 space XYZ. And we get a result. And of course, this result is also, this is a parser object. This is a parse result object. And now we can inspect it. So we could say the expected value here is ABC123. Actual is results and a getter for the output. And we can also inspect the remainder, which in this case is going to be space XYZ. Let's run that, and you can see it working. So what happens, we match the first one. This combinator actually keeps trying this parser, and then actually appends all those parsers. So we had, here we had sequence, which dropped the first one and kept the output of the second one. This one internally is using append, which is keeping the first one and then append the second one and append the third one, and etc. combining them into this. But then it encounters a character that is not alpha num, so it stops parsing and returns the rest as the remainder. If we wanted that, of course, we could do something like use sequence. Parsing actually comes with a bunch of aliases as well. So you could write sequence like this, and then continue here with, for example, this is a parser that will skip any amount of space, and then it could be another one of these. So this is one way to write it. You can write the same thing with a fluid interface. So let me import that one. Oh yeah, sorry, sequence only takes 2 arguments. But well, that would be actually a good reason to write it like this. At least one alpha numcar, followed by this is our second parser, so that's our space, followed by our last one over here, and oh, and now we have a parser that will try this. It will match the first word here, match the spaces, and just ignore them, and then match the last part and return the result of the last part in this case. So this would be our output, and our remainder would be empty, if I'm not mistaken. And there we go. All right, making sense? Any questions about this stuff so far? Because if you don't have questions, that means we're ready for doing some exercises yourselves. Let me admit some more people into the. Yeah.
I'm not sure if you already mentioned this because I only just joined, but can you compile it into like an AST?
Yes. Yeah, I actually didn't mention this. It's sort of part of the exercise, but I will show how it would work. So here, for example, well, the next thing would be how to turn, because I said we turn strings into in the beginning, we turn strings into more structured data. So of course we'd want to end up with something like an AST for a programming language, or basically something like the JSON decoder returns a nested array and objects, etc. So of course that would be a lot more useful than this stuff. So there's 2 parts to that. One is mapping. So we need to map stuff into more useful things. For example, well, let me just add a new test. Yeah, let's call it map. So let's say I have a parser that takes a digit character. That's just a single character, 0 to 9. So that's not that useful yet, but let's make numbers. So this one would actually a proper number. For example, in PHP, I think, well, this is not the same. Is not a. I'm not sure about PHP actually. This is just a 1 integer probably. But in JSON, for example, this is not a legal number. So the proper parser for this is a little bit more complicated, but for now this will work. So, but what this returns, well, let's just inspect that. So parser try on a string. And let's run that. Oh, we're in the wrong place. Oh yeah, and I need this is an annoyance for me in PHP Storm. When I want to debug this value, I cannot put I need to put something here in order to be able to put a breakpoint there. But now we should be able to see the result. So our output is 1 to 3 is a string 1 to 3, but we want to turn that into something useful because we wanted an integer parser here. So the way to do that is to use map, and map is just like array map. Maybe you're used to that one. It's a function that takes the output of that parser and transforms it into something else. So here, for example, we could use infol of wait, no, it's like this, right? Int of output. And now when we run this, we should see that our output is an integer. So basically, what this allows us to do is, of course, take the output of this chunk of the parser and turn it into something else. We can combine this now with other stuff. So this could be well. Let's just have 2 numbers and let's turn them into an array. So what we could do is here use collect. So collect is a combinator that takes a number of parsers and returns an array of all the outputs. So I could have, well, it's 2 numbers, right? So this one is, let's just call this one number, and then we can do 2 numbers with some space in between, like this. And now when we try this on our inputs, we should see that the output is now an array of the outputs of all 3 parsers. And we can combine this now with map. So we could add map here, because I said we wanted an array of 2 values, and this one has 3 values. We actually want to get rid of that space in between. So we could add a transformation here that takes the output, which here is an array, and returns a new array of the first and the last value. So that will be index 2, and like this. And now we should see that we have these 2 values. And of course, this transformation could be anything. This could be a constructor for an object, for example. And that's actually how you can build. So the nice thing about Parser Combinators is that your grammar, your language for describing your parser, and your transformations into an AST is just one step, as opposed to, for example, I think the PHP internals parser first tokenizes the whole input, and then takes that list of tokens and turns it into something else. So it's like a 2-step approach. And of course, there's going to be different trade-offs and benefits, etc. And this approach, Parser Combinators, for example, PureScript uses that, which is like a sort of a Haskell-like language that transpiles to JSON. Elm uses Parser Combinators. So there's a lot of these languages now that use Parser Combinators as their main for their main compiler. So I think that's a sign that it's a very useful and widely applicable approach. Should you do this in PHP? That's of course the other question. Right now, this approach using Parsica, it's going to be way too slow. If you compare, I wrote a JSON parser and compared it to the native JSON parser in PHP, and you don't want to know. But I think there's going to be I haven't done that much work on that yet, but I think it will be very interesting to try to build some optimizations so that Parsica is actually, becomes a valid choice for production parsing. So now you could use Parsica if it's like I don't know, some small stuff, and you're doing it. I don't know, maybe like I'm using it for a static site generator. So we only run that parser when we're when the site is being generated, which only happens when new content is added, which is maybe once a week. So the cost of a slow parser isn't that bad. But if you're going to parse millions of things a day, then don't use Parser for now. That's maybe an important caveat. But that's basically the process, right? You combine. So here we wrote a parser, and then we named it so we can reuse it. So you build up these sort of building blocks, and you combine them into bigger things. So this one is now, I don't know what this would be. Maybe this is I don't know. Let's call it 2 numbers. It doesn't really make that much sense, but as an example. But maybe our next thing could be something where we want to be able to. Let me just get rid of this so we can see what we're doing. So maybe our next thing would be I want to start parsing lists of 2 numbers. So separated by whatever you like. Of course, this could be separated by this. So this could be your input format, and so now you can combine the 2 numbers parser and separator. So you could use something like separate by character, and I'm spoiling too much of the exercises, but so this would be my separator. This is the number parser that we already have, and this whole thing we'd want it to be between opening brackets like this, another parser for the closing brackets, and then inside that is the separated by this bit, and etc. And then of course we'd have to do our mapping and etc. correctly, but this is roughly what you would need to write to parse something like this. Right? So it's actually very readable and compact and maintainable. If you compare this to, like I wrote the JSON parser and I looked at an existing JSON parser that was written in pure PHP, and the difference I don't remember exactly, but it was like I think my parser needed maybe 10% of the amount of code of the other one. So that's why I like these things, of course. But all of this is in the exercise. So the goal is now that you check out the repo. It's in the chats. Where's the chat? I lost
Could you potentially repost in the chat? Because I think when I joined,
Yeah.
it lost the history.
Yeah, I'm trying to find how I get back into the chat actually.
Yeah,
I've just posted it. It's fine.
Oh, okay, thanks. So, well, before we start, any questions so far about the whole Parser Combinator business? Anybody who maybe doesn't see the point, or I don't know.
I'm trying to think of a use case for me where I might use it personally.
Yeah. Yeah, so it's anything. So the thing I use it for in that static site generator is a bunch of date ranges and things like that. But it also does, it's more than just dates. It also does things like Q1. So if there's no date yet, but we know it's going to be in Q1, we just put Q1 2020. It parses stuff like that, and then turns all of that into an object that represents these periods. So that's like a very nice, simple use case. But yeah, you could do anything from simple string formats, file formats, to programming languages, anything really. Or even, it doesn't really support that yet. So far, it's only strings, but you could theoretically use this to build parsers for object graphs, where, for example, you already have so what you could do, for example, is use PHP JSON decode, which parses a JSON file into just plain old PHP objects and arrays. And then use Parser Combinators to turn that structure into something more meaningful in your app. So even things like that should be possible, but I haven't tried that yet.